Good day, good afternoon or evening for everyone. And it's my pleasure this week to introduce Ieke Moerdijk from Utrecht University. And he will tell us about Dendroidal Topology, an introduction to Dendroidal Topology.
Thank you very much. Thank you for the invitation, and thank you for offering me the opportunity to give this talk in a way which is still a bit unusual for me, although I've been Zooming now for an entire academic year. But it still, of course, doesn't have the same quality of communication as a live person-to-person lecture. So I wrote some pages, and we will go through these pages together. I have presented these. I wrote these pages really as a rather informal introduction for non-specialists. If you are interested in more technical details, there are a number of papers available on the archive or already published. I gave some names of my collaborators and some other people who contributed to the area in the abstract. So I'm sure you can find these papers online. I'm also writing a book with my colleague Gijs Heuts. The vowel of his first name is IJ, like in my surname, and the vowel of his surname is EU. That's also a Dutch diphthong, Heuts. So it's a bit difficult to pronounce for many of you, I'm sure. But anyway, you can find a link to a preliminary version of that book on the through my homepage, for example, at Utrecht. And if you're interested in details and further references, I'm sure this will help you along quite a bit. Okay, so the idea, as I wrote it here, is to find a combinatorial approach to topological operands and their algebras. And what I'm going to emphasize is the analogy to the way that simplicial sets are used to model topological spaces and also topological categories. So that's a very classical tool. The geometric realization of a simplicial set is a topological space, and every topological space is weakly homotopy equivalent to such a realization of a simplicial set. And if you restrict yourself to CW complexes, the relation becomes even a bit tighter. But then you have to restrict yourself to Kant complexes on the simplicial side. So this is a phenomenon of restricting yourself to cofibrant and fibrant objects in equivalent model category. And I may say something more about that as we go along. Simplicial sets are also used to model topological categories or categories enriched in topological spaces, or categories enriched in simplicial sets, which is the same thing on the basis of what I just said, up to homotopy. And this leads into the theory of infinity categories. So the way simplicial sets model topological categories is exactly the basis of the theory of infinity categories, or quasi-categories as they're also called. Very much en vogue these days, as all of you know, I'm sure. So let me go to the next page if I can. Okay, so since this is a colloquium style talk, I will remind you of various things. And the first thing is a page for those who have forgotten the definition of an operand. I'm sure that there's the minority among you, but still. And I will, rather than giving the definition, I will show you the archetypical example of an operand. In fact, the example that motivated the entire theory. and it's that's called the little cubes operand. So it exists in any Euclidean dimension D. So you have CD for every D, at least one, let's say, and it is. So this CD is a lot of information. You have topological space for every n, which you should think of as the space of operations of n variables in some sense. And in this case, it's the space of configurations of cubes inside a unit cube. So you have a unit cube, 0, 1 to the d, and you put n other cubes inside it, and they have to have disjoint interiors, and they're nicely and finely embedded, and you should number them. So the symmetric group acts by permuting the numbering of the.
Just a small question: Do you want their position to be strictly fixed, or are they just there up to changing the position slightly?
No, this is the space of configurations of actual cubes or rectangles. Okay, so
you mean
of course it has a topology through which the cubes can move.
Okay,
if you
but they are fixed. Yeah, okay.
Yeah, so this space is homotopy equivalent to the space of configurations of n points in RD.
Yeah, okay, fine.
Configuration space just by taking the centers. Okay. So here's a picture. So this is the unit cube in the picture in dimension D, of course, and this is an element of C2, 2, okay, 2 cubes. Is also an element of C2, 2, and besides permuting the numbering, there is the operation of substitution or composition, as it is called, okay. And if you have k cubes and you select one of the cubes here, cube is maybe a bad word, the ith one, then there is a composition called circle I, and it consists of copying this configuration inside the ith configuration. So this is I is 1 here, and then you get this picture, and then you forget the ambient rectangle here. Okay, so that's a substitution of pictures. You have to rescale so that it fits, of course, but that's all. Okay, and then you can write down some axioms of associativity. There will be a unit operation, which is just the configuration consisting of one cube which coincides with the unit cube. And there are some axioms expressing compatibility of changing the numbering of the cubes and substitution. So why is that an important object? Well, there's the notion of, for any opera, there's the notion of an algebra. So in this particular case, I said already, you should think of this space as the space of n-ary operations. So these n-ary operations act on a space through maps like this. You take n points in X and you hit it with an operation and you get a new point in X, okay? And then there are sort of obvious axioms relating to the composition that we had before. Composition in the opera should correspond to composition of these action maps, okay? And I call it here the mother of all theorems about operats. I don't know whether that's well, I think it's correct in a way. Namely, this notion of operat, and in particular these little cubes operat, exactly describe spaces that have the structure up to homotopy of an iterated loop space. So that was it was on the previous page. I will not scroll back, but that was a discovery of Boardman and Vogt and of Peter May. Boardman was at Johns Hopkins, and he recently passed away, as some of you may have seen, sadly. And last time I met Boardman is a while ago, and it was another sad occasion because it was at a memorial conference for Rainer Vogt, at which I gave a lecture. So this brings back sad memories for me. Anyway, so here's an explanation again of what I mean. What does it mean for X to be a default loop space? It means that there exists a space Y, such that if you take the loops and then the loops of the space of loops and so on, D times, you get something which is homotopy equivalent to X. Okay. What I'm saying is not 100% correct, because this is, for those of you who know the technical words, this is true up to group completion. But within connected spaces, for example, it's literally true. Okay, so that's just a little motivation for theory of operands. Here's one other example, which is actually, it looks completely different, but it's closely related to the previous example. The symmetric groups, sigma n, also form an operand, because you can substitute, if you think of the elements of sigma n as permutation matrices, you can substitute the ones in a matrix by substitute matrices for the ones in another matrix, and this gives you exactly the operand structure. So I could quickly go back. Where is my circle operation here? If you have an n by n matrix and you pick a factor I, then you can take the ith one and you can substitute the k times k matrix there. This gives you the structure of an operand. Okay. Now the nice thing about operands is that if you hit an operand in a category with a functor, and this functor preserves products, or it sends products to tensor products, if you want to move into a slightly more general situation, you get another operand. So it's a very flexible notion that can be moved from one category to the other. And in particular, if you take the classifying spaces of the symmetric groups, for example, then you get an operand, but you lose the sigma n action. However, if you take the contractible space with a free sigma n action, so that's the total space of the classifying bundle over the B sigma n, then you get a space, and these spaces again form an operand, and this operand is called the Barrett-Eccles operand. That's why I denoted BE. And the BE algebras, the Barrett-Eccles algebras, are exactly the infinite loop spaces. So there are those X for which you can do this for any D. You have found your Y for a D, and then you can find D loop further, as they say. So this Y is again the loop space, and so on. So it's infinite loop spaces. Okay, so that's my mini introduction to operands. And now a quick reminder of simplicial sets. Now, I'm sure you all know the theory of simplicial sets, but don't fall asleep, because what I would like to emphasize is the analogy between simplicial sets and dendroidal sets. So all the things that I'm going to talk about will come back in a slightly more complicated form. Nonetheless, I think we can go through this relatively quickly. So delta is the famous category of finite non-antilinear orders and monotone maps. And usually one takes a skeleton. So the objects are brackets n. So that's the linear order 0 up to n. And the morphisms are order-preserving maps. And there are maps that one can focus attention on, namely the map from n-1 to n, which is an injection which misses I from its image. So you can do that for I 0 up to n. And the map from n to n-1, which is a surjection, and it has j twice in its image. And you can do that for j is 0 up to n-1. You see my arrow, right, John?
Yes, we can see your arrow. So
Yeah,
Ieke,
okay.
there's a question in the chat about operand. So it said, is there operand for suspension?
For suspension? I don't think so. I have to think. I haven't seen it.
Thank you.
Okay, so a simplicial set is a functor from the opposite of delta to sets, and there is some standard notation for such an object. Namely, one writes x sub n for the value of x at this object brackets n, and the contravariance is denoted like this. If you have a map alpha from n to m, then it induces a map in the other direction, so from xm to xn. And that's usually just denoted alpha upper star. And in particular, for these two maps that we have here, we have the phase maps, di from xn to xn minus 1 to xn, and sj from xn to xn minus 1. Okay, these maps, this is in fact a split mono, and this is a split epi. So di, since it's contravariant functor, di will be a monomorphism, which in fact has a retraction, and sj will be an epimorphism which has a section. Okay, relevant for us is the example of a nerve of a category. So the geometric realization of this particular simplicial set, the nerve of C, is the classifying space of C. And one way to define it is by saying that its value at n is the functors from n to C, because n is a linear order, so poset, so you can partially ordered set, so you can view it as a category. And in this way, you make it completely evident that it's contravariant in n. Okay, so the slogan that simplicial sets model spaces is, I said it in the beginning, one way to say it is that the homotopy category of spaces, or maybe of W complexes, is equivalent to that of Kant complexes. So I also want to say a word about Kant complexes. So what's a Kant complex? A Kant complex is a simplicial set which has the special property that if you give some phases of an intended simplex, you can actually find that simplex. You can extend that to a simplex. So here's a picture. If you're given an element of x1 that looks like this, and an element of x1 that looks like this, so the endpoint of one of the phases of one is also a phase of the other. So you have two elements of x1 which agree in x0. Then you can actually extend that to an element of x2, an element of x2 that has these two as two of its faces, and the third one which is left open, free to choose, so to speak. So here's a more formal definition. You can, this is the representable standard notation for the representable simplicial set. So it is it's like the n-simplex. It's the analog of the topological n-simplex, but then in the world of simplicial sets. And this is the union of all the faces except one, and the one is the one opposite the kth vertex. And if you have a map like this, you can always extend it like this. Okay. So here's another way you can say that there is a map from xn to some inverse limit, which I will picture below, and that map should be a surjection. Okay, if I go down a little bit, then here's the definition of this horn. It's called the K horn, or the kth horn. Okay, so it's the union of all the faces delta m inside delta n that contain the vertex k. So the only one that is missing is the one opposite the vertex k. Okay, so these Kant complexes are quite important because if, for example, mappings into a Kant complex, for mappings into a Kant complex, the homotopy relation is an equivalence relation. And you can define homotopy groups in a completely combinatorial way, and you can in fact show that these have a group structure. You can add elements there purely inside the simplicial world, and you cannot do that if your X is not a Kant complex. So here is an example of simplicial set that we would like to be a count complex, the nerve of C, but it's only a weak count complex because it will only have this extension property if K is different from 0 or N. Okay, so it will only hold for interior Ks, inner Ks. Okay, so these weak count complexes, they were already, their importance was already realized by Bortman, in fact, and but nowadays they are rather known under the name of infinity category or quasi category, and these notions have been emphasized by Joyal and Lurie and many others now. Okay, so there's an important weakening of a count complex. Okay, so that ends my introduction to simplicial sets. And now the talk will start, in a way. So I'm going to introduce a category omega. And you should think of this category as a category like delta. Okay, but the objects, instead of finite linear orders, they have finite rooted trees. I will draw some pictures. I think there are, if I scroll down, you will immediately see some pictures. If I draw a picture, it will automatically be a planar tree, but I don't mean these trees to be planar, as is obvious from the first type of morphism. What are the morphisms in these trees? They are generated, so they're compositions of 4 types of morphisms. And these types of morphisms, they are like the DIs and the SJs of the simplicial category, but except for the fact that we also have isomorphisms. So everybody knows what an isomorphism is between trees. I don't need to say anything. And then there are 3 other types of morphisms. There are interfaces. They contract an edge in a tree. There will be a picture in a minute. There will be outer faces or external faces, and they chop off an outer vertex from a tree. And there will be degeneracies. Degeneracies that sort of collapse unary vertices. So let's slowly take this in. So I drew a picture. with these morphisms. So let's slowly go through this picture because this is important. So let's look at this tree. Okay. So it's a tree. It has a root. It has leaves, 4 leaves, and it has vertices. These vertices have arities. So this one has arity 2. So this, in graph theory, one would say usually that the arity is 3, but I'd rather take the arity as the number of incoming edges oriented towards the root. So this has arity 2, this is arity 3, this one is arity 0, that's allowed. This is arity 2, okay? And now this A is an inner edge. I can contract the edge A and I get this picture of the tree, okay? You just contract this edge. If I didn't make a mistake in drawing the picture, and there is a morphism in this direction, okay? You can also chop off an outer vertex. So there are several outer vertices here. For example, the root vertex. And if you chop off the root vertex, then you will get this tree, and there will be a map this way. And you can chop off the V on top. You can get the map this way. I could also have chopped off this vertex, but I didn't draw that arrow. And of course, there are all kinds of relations between these morphisms. I think you can imagine that if you contract A and you chop off V, these have little to do with each other. So if you do both, you get this picture and you get a commutative square. And here is a so-called degeneracy. The degeneracy is, it picks up a unary vertex like this one, and it just erases it. Or in other words, it identifies these 2 edges, okay? And you get this tree. That's a degeneracy. And there are sort of obvious commutation rules. There are other ways to define this category in a more global fashion. Maybe I will get to that at some point. Okay, and a dendroidal set will be a contravariant functor on this category. So for every tree I have a set, and if I have a morphism here, I can move backwards in the dendroidal set. So we'll probably look at this picture again, or similar pictures. Here is an example. So for simplicial sets, we took the nerve of a category, and now we can take the nerve of an operand. Okay, and so if you have an operand, I will just take a discrete operand just for this example. Then so I have these operations. I will get a nerve, and what is this? So this nerve will have to assign to every tree a set. Okay, and the set is given by assigning. Given the tree, you assign an operation of the right number of inputs to every vertex in the tree. Okay, and then you have to show that it's functorial. And I think this is just an example. So look at this. This is the picture in omega here. And here is an element of the nerve of P at this tree T. So it assigns an operation P in P2. Here it is. A Q in P3, an S in P0, and an R in P2 again. And then I have to define what the action is by this arrow. So I have to find a similar labeling here. Okay. But I've these two vertices are now just one vertex because I've contracted A. And so I assign to this new vertex, this contracted vertex, so to say, the composition P circle 1 Q. Okay. Now you may object, so I will pause for a minute and raise a point of slightly technical point. So just ignore it if you get confused. But why is there a 1 here? There's a 1 here because this is on the left, 1, 2. But this makes use of the planar structure. And I told you that the trees are not planar. So if I want to give a more precise definition, I should say an element here is an equivalent class of a planar structure on the tree and such a labeling. And if I change the planar structure, if I flip these two edges, I should replace this P by P times the permutation in sigma 2, which acts on the operand. Okay.
Can I ask you one stupid question here, which is that in the case of simplicial sets, you had a very nice presentation of the nerve of a category by looking at functors from N to the category. So is there something similar like an operand structure on trees on root?
Absolutely, absolutely. So maybe it's even a few lines below, but I don't remember what I wrote. It's one day ago. So such a tree generates a free operand.
Okay.
And but it's a colored operand. So you have operations which whose inputs, the operations of n variables, they have their inputs have different types. And the types are the edges. They're called the colors usually in this theory. So the colors are the edges, and then the operand is generated by a binary operation from these two edges to this edge, and a ternary operation from these edges to this edge, and so on. So there's a free operand, and just homing out of the free operand will give the nerve. So the answer is yes. Okay. So there's also a notion of, so this is a next example. I said the nerve of an operand is a dendroidal set. The nerve of an algebra will also give a dendroidal set. So if you have an algebra A, so for the operand P, it's given by maps like this, satisfying several identities. and I will write the application just as if it is the application of a function like this for the notation. And then you can define another dendroidal set, and it's very much like the one before, where I label the vertices by operations in the operand, but I also label the edges by elements of the algebra. Okay, and going down the tree, you have to follow the application of the operations of the operand to this algebra A. So you start by labeling the leaves. I give an example. I label them by A, B, C, and D, elements of the algebra. And then I have to label this edge by R of AB. Okay. And I have to label this edge by S of nothing. Okay. So that's a constant in the algebra, and so on. And if you do this, you can see that this is again nicely factorial, precisely because of the equations. For example, here I wrote something. So this is P of Q of something, but it's also P circle 1Q of something else. And you have to use that to show that it's nicely factorial.
So Ieke, there is a question in the chat for you.
Yes.
So the question I just read, just to check if I understand, do I see that the trees we are working with here don't have to have a zero array vertex at every leaf?
That's right. That's right. So in fact, the leaves are, so sometimes by operatic people, these are called half edges in graph theory. These are half edges. These are sometimes, I call them stumps sometimes. So you should really think of these as inputs of some operation, and these as constants of some operation, some structure. So it's trees with half edges. That's one.
Thank you. That makes sense. Thank you. That makes.
I cannot scroll while I have to admit somebody. Apparently. Okay. So to get a bit more intuition of what's going on, there is an inclusion of delta into omega, very easy one, because every linear order can be viewed as a tree. So you have to pay attention because there is this number n, and the corresponding tree has n vertices and n plus 1 edges. So I number the edges 0 up to n. Okay. And this inclusion is in fact of a very simple form, because delta is isomorphic to the slice category in omega, the slice over a specific object eta, and eta is the tree with no vertices. I didn't emphasize that earlier, but there is a tree whose only leaf is also the root. Okay, and that's also under this inclusion, it's the tree corresponding to the 0. So as a consequence, every dendroidal set has an underlying simplicial set, because if you have a contravariant functor here, you can just restrict it to delta. And every simplicial set can be viewed as a dendroidal set by the left joint of this restriction, I shriek of M. And I shriek of M, you should just think of extension by 0. I probably wrote it somewhere, yeah. Okay, and if you look at this picture, the notions of inner and outer phase and degeneracy, they for omega correspond exactly to the traditional ones for delta. Okay. Right. So one of the big complications of the theory compared to that of simplicial sets is the fact that there are lots of automorphisms, and at some point you get into all kinds of the subtleties of equivariant homotopy theory at some point, not in this introductory lecture, of course. But because of this, it's very important to have a very good grasp on the morphisms, and to this end, it is really helpful to emphasize a few points. Namely, if you have a morphism in omega from S to T, so S and T are two trees, and the morphism is called alpha for some reason, then it sends edges of S to edges of T. We'll look at the pictures later on. But it does not send vertices of S to vertices of T. Rather, it sends vertices of T to vertices of S. And only partially so. So it's a partial map in the other direction. And it's also a partial map on the leaves. Okay, so that's important. Maybe before we look at the pictures, let me, maybe for the leaves, if you have a map from S to T, you could think of S as some sort of subtree of T. And then if you have a leaf of T, you look at the path from that leaf to the root. That path could enter S, and if it does, it has to enter S in the leaf. And that's the value of this map here. And if it bypasses the tree, the image of the tree S, then the map is undefined. Okay. Now, this category of so the leaves is a functor from omega to the opposite of the category of finite sets and partial maps. And that's a very famous category, this opposite category. That's the category gamma, yeah, so of Graham-Siegel.
Exactly, because it's like taking pointed finite sets and then taking the opposite category. Yeah.
Exactly. That's gamma. So finite sets and partial maps is the same as pointed sets and total maps, of course. And if you throw away the base point, then you get partial maps. Okay, and this is also, I will say something about this at the end maybe, but this is also the relation between dendroidal sets or dendroidal spaces and gamma spaces. Also shows that these dendroidal sets can be used as what is called an infinite loop space machine. Okay, so let's just to emphasize this a little further, let us look at pictures. Okay, so is that the picture I want? No. So if I contract an edge, that's this map here, then of course I have a map from the edges here to the edges here. It's an injective map and it just misses this A. Okay. But if I now look at the vertices, this vertex here is in some sense the composition of these two vertices. So I get the map in the other way, which sends these two vertices to this vertex here. Okay. And if I chop off the vertex V, here I would like to get a map in the other way, but V is no longer here. So this map is undefined on V. If I go all the way here, then on the vertices, it's undefined on V, and it sends these 2 points to this vertex here. Okay, so that's how it works. Can I show the partiality of the leaves here? Not clear to me. One, two, three leaves. I've lost a leaf here. Oh, yeah, but these two leaves go to the same leaf. Okay, I don't think that I should have thought of that. But you can imagine that if you cut away larger parts of the tree, then you miss leaves. So this is the category omega. By the way, about these half edges, there are many variants of omega. You could take trees without these half edges, without leaves. That's very good for operats which have a constant in degree 0. For P0 is a point. You could take trees which are open, which have no nullary operations. You could take trees without unary vertices. So these are variants, depending on the type of operat you want to study, these are variants that come up very naturally. So don't take this category omega too dogmatically. Okay, so now one can define dendroidal weak count complexes. So I'm calling these infinity operats, just like the simplicial weak count complexes are called infinity categories. And the notation is very similar. There is, for every tree T, there is a representable, which I denote, instead of delta bracket N, I denoted omega bracket T. So here is the definition of the representable phantom. And this representable has a boundary, and it also has a part of the boundary which misses one face. And it misses the face which contracts, which would have contracted an inner edge E. Okay, so there is the union for, you take all the maps from S to T, and you take their images, and but the only one you don't take is the one where the edge E has disappeared. So E, the edge E must still be in S. You get another tree S, omega of S, it embeds nicely into omega of T, and you take the union of all those. And that's the horn, the inner horn. Okay, and there is a similar, you could also take the part of the boundary which has all the faces except the one that chops off a top vertex. That's, we call that a top horn or a leaf horn or a left horn. Various terminologies en vogue. So then one can define an infinity operat to be a dendroidal set X, which has this extension property. Okay, and you can check for yourself that the nerve of an operat will always have this property. Okay, and if you look at this map, the nerve, remember the nerve of an operat where you also label the edges by elements of the algebra. I'm rotating my, sorry. It has more structure, so there's an obvious projection there, and it also has a specific property. It has a lifting property of this kind. So if you take an inner horn or a left horn, but inner horn is sort of automatic from what I said before, but a left horn, you will have this lifting property. Okay, and if you know something about Quiller model categories, then it's full of axioms and things to check of this kind. So this is what is called the left vibration.
But you mean that you have a model structure on the?
Yeah, that's the, yes, certainly. That's okay. I will come to the model structures in a minute. But before that, I want to say something because I started out by saying that dendroidal sets model topological operats, but so far we've only talked about discrete operats, set operats. So what do we do with topological operats? And how do I get something set-like out of a topological operat? So this is what I would like to explain. And it goes as follows. So I told you before, I mentioned, but it was not on the slides, but I mentioned in response to a question by Alain that every tree defines a free operat, which I provisionally denote free of T. But this free of T, there's some sort of topological resolution of this free of T, W of T. It's in fact a special case of a much more general construction called the Boardman-Vogt resolution of an operat. It's also, some of you may have seen in a slightly different context, the Kobar-Bar resolution of an operat used by many people working with this sort of thing in a linear context, and this is the topological analog of that. So so W of T in this context is a very simple thing. It is a colored operat, and the colors are the edges of T, and so it should have n-ary operations now where you take n inputs given by colors, and the output has a color. So I'm going to define, so this is my P, so to speak, and instead of just an n, I have a sequence like this. And W of t of E1 up to n E, and most of the choices for these edges will be empty. It is non-empty if there is a subtree of t with leaves E1 up to En and root E. And in that case, it will be a cube. And is in the following picture. So if the situation, if the E1 up to En and E are positioned like this so that you can draw a tree, then this is the space of length assignments to the inner edges of that tree. So here's an example. This is again the same tree that I've been drawing all the time. It's my edge A. So if I just take E1 and E2, there is no tree which I can draw with leaves E1 and E2 and edge A, because I somehow need this input E3 to be able to reach A. But if I take E1, E2, and E3, and I want to move to A, there are inner edges. Okay, there is an inner edge here, but don't forget, here I don't need an input at all. And so this is also an inner edge which lies above A and is inside this tree somehow. I should have defined this a bit more technically, but I hope you understand what I mean. Okay, so the space of operations from E1, E2, E3 to A is a two-dimensional cube. Okay, and this is a functor. If the chopping off vertices, it's obviously factorial on chopping off vertices, and for inner edges, it comes down to assigning length 0 to the contracted edge. And then if you have a topological operator P, you can take, so the nerve of P would have had here home of free T to P. But now I take the home from this resolution of T to P. I call that W upper star of P, and that's the homotopy coherent nerve. Okay, let's try to see. Let's try to understand a little bit this terminology. I think it's on the next page. There's a little theorem that this will always be an infinity operator. This is, I think, a lie, because you need the spaces of P to be Kant complexes, but never mind. Just why is it called the homotopy coherent nerve? Let's look at the value of W upper star of P at this tree T. Okay, it would have an operation for P, an operation for Q, but also an operation for the composition R. Okay, and then there would be a path from P circle 1Q to R. Yeah? So you sort of give a candidate for the composition, and then a path like a homotopy from the actual composition to the candidate composition. And for larger trees, you get what are called higher coherences. Okay. Now this functor. Now here's the first theorem. This functor W upper star induces an equivalence from the homotopy category of topological operators to the homotopy category of dendroidal weak Kant complexes. And there is a similar theorem. The homotopy category of P algebras. So these are really topological guys, and these are very set theoretic objects, discrete objects, combinatorial objects. For P algebras, there's a similar theorem, but now you have to, instead of weak Kant complexes, you have to you consider these left vibrations over W upper star of P. Okay. Now, if you, I will come back to these theorems in a slightly more technical fashion. But I just want to point out, just to prove that there is some content to this, there's a trivial operation that you can do in this context, namely slicing by eta. And I told you before that we get delta. And over eta, topological operators will become topological categories, and dendroidal sets will become simplicial sets, and you get this famous theorem that the homotopic theory of topological categories is the same as the homotopic category of simplicial weak Kant complexes. That's known also under the name of the equivalence between simplicially enriched categories and infinity categories. Okay, and here I also mentioned for the special case of the Barrett-Eccles operator, you can deduce that because you know that BE algebras are infinite loop spaces, that dendroidal left Kant complexes, they're left vibrations over the Barrett-Eccles operator, but the Barrett-Eccles operator is completely contractible, so you can just erase it, so to speak. Dendroidal left Kant complexes are the same as infinite loop spaces. So those are somewhat rough formulations of sort of the central beginning theorems of the theory. And this I should mention here the name Cieszynski. I proved this theorem with Cieszynski a while ago. Okay, so 2 more slides to go. I will wait a second. So one way to make a much more precise theorem. Somebody's in the waiting room and that prevents me from scrolling. There we go. Is to use the theory of Quillen model categories. So for those of you who have perhaps slightly forgotten the definition, here is some rough impression. So a Quillen model category is a category with a little bit of extra structure, namely 3 classes of maps: cofibrations, fibrations, and weak equivalences, and axioms. And there are 4 or 5 axioms, depending a bit on how you count. And one of the central axioms is called the lifting axiom. And it says the following: if you have a commutative square in your category, and this map is a cofibration, this map is a fibration, the horizontal maps are arbitrary, then if one of the 2 is a weak equivalence, is in addition a weak equivalence, then a diagonal filling exists, making the 2 triangles commute. It's called the lifting axiom. So in fact, it's 2 axioms. One when the cofibration is what is called a trivial cofibration, meaning it's also weak equivalence, and one where the fibration is a trivial fibration. And if you have this structure, you can universally invert the weak equivalences, very much like in a ring of fractions, to get a new category, and that's the homotopic category of M. Okay, so one of the inventions of Quillen was that this extra structure of the cofibrations and fibrations helps you to understand that this category actually exists, that you don't run into set theoretic problems if M is a large category, like the category of spaces, and also that you can actually calculate with it. So, and he used that to, for example, well, here is a basic example. Simplicial sets has such a model structure. Topological spaces has such a model structure. And the functors, geometric realization and singular complex, they're adjoint functors. They preserve weak equivalences. Well, more precisely, they factor over this operation of inverting the weak equivalences. And you get an equivalence of categories from the homotopic category of simplicial sets to the homotopic category of topological spaces. Okay, so that's 1960s Quillen, but this is not just an equivalence of categories, but it has lots of nice properties because of the fact that it came from an adjoint pair of functors here with special behavior with respect to the cofibrations and the fibrations. Okay, and so one says that's also equivalent. One says that simplicial sets, topological spaces, they are both models for the same homotopy theory. And with this terminology, he constructed his famous models for rational homotopy theory, for example. So this basis of this theory is really the rational homotopy theory paper of Quillen. Okay, and the theorems I just quoted are actually of this form. So maybe I'll go back to them. So there is a model structure on topological operands with a very natural notion of weak equivalence. And there is a notion of, there's a model structure on dendroidal sets, where, for those of you who know, the fibrant objects are exactly those infinity operands or dendroidal weak Kant complexes. And there is such a pair of adjoint functors, of which this is the right adjoint. So this is a little bit analogous to the singular complex that I just showed you. It has a left adjoint, which is a little like the realization. So that's the realization of a dendroidal set as a topological operand. And the situation, and it's very similar here. There's a Quillen adjunction. And this, to give you another example, I had, let's scroll up to gamma. This functor here can be used to define a Quillen adjunction between dendroidal sets or dendroidal spaces, well, and gamma spaces. And it will give you, for a slightly different model structure, what is called the Bousword localization of the original one, it will give you an equivalence between dendroidal sets and gamma spaces. And gamma spaces with a model structure which makes it equivalent to infinite loop spaces. So that's a slightly more, just in words, a slightly more precise way of expressing what I mumbled before. Okay. I have 2 more minutes, so I just wanted to give you some pointers to a few uses. There's a well-known problem in operand theory, namely how to calculate the derived mapping spaces between these little cubes operands, and in particular they have nice connectivity properties. This means that the homotopy groups vanish up to and including d-1. And this is a PhD student of Michael Weiss in Münster, who proved this theorem just by using this dendroidal formalism and somehow building towers by truncating these trees, building towers of fibrations and doing very well, I cannot say simple, but standard manipulations to get this result. There are other, Wielwacher and his collaborators also made a calculation like this, but they used Kontsevich integrals, and it only works over the rationals and so on. So this, I thought this was a much nicer approach. Another use of recent use of it is a paper by my collaborator, Boavida, but I was not involved in this at all, with Geoffroy Aurel, where they, I think there's several versions of this in the literature, so I do not know to what extent this is, well, it builds on known results, let's say, but certainly in this form it was new. There is an operand of which you can take the profinite completion, and then you end up with the Grothendieck-Teichmüller the Teichmüller group, profinite Grothendieck-Teichmüller group. And to prove this theorem, you need to analyze, I wrote here the homotopy automorphisms, so they are, maybe I should have said self-equivalences. But to calculate these self-equivalences, they immediately jump to the nerve. First of all, pro-finite completion doesn't make sense for operats, you don't get an operat. So you have to move to this dendroidal world, because pro-finite completion doesn't preserve product. So you lose the structure. The fact that it works for groups is somehow an exception. Finally, there is this very intriguing, I could have given an entire lecture about this, but there is a nice tensor product on dendroidal sets, which comes from shuffling trees instead of shuffling linear orders. And it's combinatorially very mysterious, but it has homotopically has very nice properties. So, for example, while the tensor product of operats collapses lots of stuff, if you take the operat whose algebras are associative algebras and you tensor it with itself, you get the operat whose algebras are commutative algebras. So this is the tensor product also introduced by Boardman and Vogt, and you could remember it in the following way. If you have two operats P and Q, P tensor Q is the operat whose algebras are P algebras in the category of Q algebras, or Q algebras in the category of P algebras. These two things are the same. So they're algebras with two structures, a P algebra structure and a Q algebra structure, and somehow these structures distribute over each other. Okay, but this is homotopically not a very good operation, but if you do it inside dendroidal sets, so I take this W upper star, which, because this is discrete, is just a nerve, so it's not a very complicated thing, and I take the tensor product with itself, I get a model for the two cubes operat. Okay, so it works much better. But there are lots of things to be understood about this tensor product. I think it is true that Rainer Vogt spent much of his life trying to understand this tensor product of operats, and it has many mysterious aspects. So and some of these mysterious aspects certainly remain in the dendroidal world. So there's lots to be studied here. So with this open end, I would like to thank you for your attention and stop here.
Thank you, Ieke, for this very enlightening lecture, very, very nicely given to us. Yes, I'd like to ask if there are any questions.
Yes, I have three questions. I am sure you will know the answer to the first two, but I hope you don't know the answer to the third one. Okay, so my first question is that when one looks at the preshift topos, which is associated to the simplicial category, I mean, it's known that it is a classifying topos, say, for the theory of intervals. Is there something similar for dendroidal sets for the category omega?
I know this question, but I don't know the answer. When we, at the very beginning of the theory, I thought a lot about this. And I believe the fact that there is perhaps no natural answer, or I couldn't find a natural answer, is that the Cartesian product in this topos of presheaves on omega,
yeah,
is not the right structure to reflect this operatic nature. You should replace the Cartesian product by the tensor product.
Okay.
And then try to take it from there.
Okay.
So I'm aware of the question, but I don't know the answer.
Okay. Okay. Second question, which you know very well that when you take simplicial sets and view it as a preshift topos, if you look at cohomology or homology on this topos, you have a direct link with Hochschild homology for algebras and so on. So is there something similar in the dendroidal situation?
Yes, there is. So you can develop a homology theory for such a billion presheaves on omega, let's say.
Yeah.
And in a special case where you take the nerve of an operand, you can organize it in such a way that you get the usual homology of operands. That has been bar homology of operands.
I see.
It satisfies a causal duality. It is related to deformation of operands and so on. So there's a nice theory there.
I see. Okay, and my third question, so I'm sorry to, so my third question is not a question, it's more like an interrogation. The interrogation is the following. After all, when you take a rooted tree, you have a tree which is oriented by the fact that you are going towards a root, okay? And when you look at the slice case, I mean the case when the tree had no branches at all, which was the case of the category delta, then I was wondering whether there could be, okay, so let me make a very, very brave, but probably wrong guess. You see, when you take the cyclic category, it contains the simplicial category and has the additional properties that it's self-dual, that it's isomorphic to the opposite category. So what, by looking at your graphs, I was wondering whether by extending trees to oriented graphs, what would happen? Because, so if you want, when you have an oriented graph, you have a bunch of trees inside, of course, which are, and but okay, I mean, of course, I mean, oriented graphs is a very, very big extension. So I don't know exactly what is going on. So did you think about something like that?
Well, what we did think about is, and maybe that's partially in the same direction. We did think about extending this to capture the theory of cyclic operands.
Yes, yeah.
So disregarding the fact that the root is the root.
Of course, yes. Yeah.
Or rather, one nice way is to formalize this is by sort of doubling all the edges, giving them two directions.
I see, yeah.
And then you can run through your tree starting at any or ending at any point, which is then the new root. Right. You can rotate the tree and so on. And that's a very nice way of getting a theory of cyclic operands. And it has been worked out by a PhD student then in Bonn, Tashi Walde. He's now in München, postdoc in München. But
yeah,
so that can be done.
Yeah, but it doesn't quite correspond to what I had in mind. What I had in mind when you had written this vertical tree was to make it into a circle, of course. And you know, so that it wouldn't be a tree anymore. I mean, it would be it would really be a graph, and to see what I mean, you know, in which in which family of graphs this would continue to make sense. I mean, with the various iterations and so on.
Yeah, this people also this related to the theory of modular operands.
Yes.
And I think people are thinking about this, but I'm sure there's something there, but it has not been worked out yet, to my knowledge.
Okay.
I'm not running away, but I'm turning on the light here. It's 9 in the evening here, mind you.
More questions?
Wait, he's coming back.
Yeah, I know. Just to be. Yeah, I was wondering if this enlargement, this category that you have described to us has been taken up in algebraic geometry. I mean, you mentioned this homology process, but it has been taken up in this derived version of algebraic geometry. If anybody has implemented this, your point of view in derived algebraic geometry.
I don't know. I know that at an early stage of the theory, Bertrand Thoin had several constructions of which he wanted to, exactly in derived algebraic geometry, where he wanted to establish an operatic structure, and the operatic structure was too weak. It was too much up to homotopy to actually define a strict operator. So he used this category omega to make explicit this operatic-like structure.
This weak equivalence. I mean, because otherwise one loses a little bit control of the intuition of what is relation between, I mean, involving weak equivalence. How can I understand weak equivalence more explicitly? Or something.
Yeah, I can give you the formal definition, but maybe it's more enlightening. So first of all, if you think of simplicity enriched categories, or topological categories, I will first tell you what the weak equivalences are there for the model structure. Okay. So first of all, if you take pi0, you take the connected components of all the home sets, you get an ordinary discrete category. Yeah, just a category in sets. So a weak equivalence between topological categories should induce an equivalence of categories after having taken pi0 at all the home sets. That's one condition. And the second condition is that it is what you could call homotopically fully faithful. So if you take two objects in the first category and you take the space of maps, space of arrows between them, you map that to the second category, you just have a map between spaces, and that should be a weak equivalence of spaces. Okay. Now you can write down the same definition for operators, except that the mapping spaces are a bit more complicated. They go from n points to 1 point. And those are the weak equivalences that feature in this theorem. Where is it? In this theorem here. Okay. And since I gave you the definition, this the W upper star, you could use W upper star to define the weak equivalences here, but that's not exactly the way we do it. We first define these vibrant objects, and if you have the vibrant objects in a category, then you could also define the weak equivalences by testing them, by mapping into these vibrant objects. So that's how we define them. But the intuition that I gave you earlier, which is a little bit like fully faithful and essentially surjective, is I think perhaps more helpful at this stage.
More questions? Any other question in the chat?
I will stop sharing so that I see some of you.
So I don't see any question mentioned in the chat besides the first two. So I guess we thanks a lot, Ieke, for the talk. Very nice talk.
Very nice talk. Yeah, thank you.
Yes.
Well,
Thank you.
Thank you for offering me the opportunity.
Thank you. And I pass the chat to Zhang, who will probably announce for next week something in the seminar.
I shall have a glass of wine now.
You deserve it. Yeah, well deserved.
Thank you.